Calorimetry. This is where we're going to be using the system and the surroundings, measuring the surroundings so we can figure out delta H. So the law of conservation of energy essentially says that the change in energy of the universe is zero. So there is no change in energy. Whatever amount of energy there was at the birth of the universe, there is now the same amount of energy now, and there always will be. There is no destruction of energy. That's what the law of conservation of energy is saying. So if you divide the universe up into the system you're interested in and everything else, the surroundings, then those two values, when you add them together, their sum must also be zero. So we can then say, well, in relationship to each other then, whatever amount of energy is moving out of the system has to be the amount of energy gained by the surroundings, or vice versa. Essentially, the change in energy of the system is equal but opposite to the change in energy of the surroundings. So any change in the energy of a system is accompanied by an equal but opposite change in the energy of the surroundings. So what the system loses, the surroundings gains, or whatever the surroundings gain, the system will lose. So we can write it like this. Same idea, but specifically we're talking about the enthalpy change of the system, often a chemical reaction. If it is gaining energy, it has to be getting it from the surroundings. And we're going to talk in relationship to the heat that is moving out of the surroundings into the system, or vice versa, out of the system into the surroundings. Again, it is an equal but opposite change. We can talk specifically about a particular delta H, a particular molar delta H. And remember, for molar delta H's, you're talking about a specific change for a specific substance, and it is specifically for 1 mole. So if you want to deal with any amount, you can just factor in the number of moles you are talking about with the molar enthalpy, and that'll give you the entire delta H of the system. And heat itself, you can't really measure it directly, but what we can do is we can measure a couple of things about the surroundings and calculate out what that heat is. And so instead of just using Q, we can measure the temperature change of a particular mass of a particular substance with a certain specific heat capacity, and that will give us the heat that is moving in or out of that surroundings. And so generally, again, we have the system that we're going to be talking about as a chemical reaction or a change of state, and we can use the molar enthalpies for that. And then we are going to take the measurements of the surroundings so we can see, okay, is energy moving into the surroundings or out of the surroundings, and therefore we'll know what's happening with the system. Do note that this X is standing for the particular molar enthalpy for a particular change. For calorimetry questions, we're going to make two major assumptions. Essentially, we are going to imagine that no heat is lost. So we're pretending we're dealing with an isolated system. We know it's not going to be perfect. We will lose some heat, but instead of doing all the work and try to figure out what that little amount is, we're just going to ignore it and pretend it's not there. Sometimes we may state that the calorimeter, the container that the reaction is taking place in, might absorb a certain amount of energy, so we'd factor that into the particular question. But unless we're otherwise intending to do so, we're assuming all of the system's energy is moving into or out of the surroundings, and just the part that we're actually measuring, not the container or the table or the air around the table or the house next door, but just the particular part of the surroundings that we are currently measuring. And the rest is negligible, we can ignore it. And then for dilute solutions, we're going to assume that the heat capacity, if it's a dilute solution, we'll say it's got the same heat capacity as water, so that's the 4.18 joules per gram degree Celsius. If we're putting it in joules and grams degree Celsius, again, that could also be 4.18 kilojoules per kilogram degree Celsius, or you could put it in other units, but for the most part, we're going to stick to using joules, grams, and degrees Celsius. The density of water as well. So we're saying that if you have 1 milliliter of water, it's pretty much gonna weigh 1 gram. So we're making that assumption that the density of water is pretty much 1 gram per milliliter, and if it's a dilute solution, it's going to have that density as well. So particularly looking at the heat of solution or dissolving of an ionic crystal into water, into a solution, to make a solution, there's sort of two steps that we need to consider. First off is we've got the crystal and it's held together with forces, and so it has a certain amount of energy. The water, hydrogen bond to itself, also has a certain amount of energy. So we're starting off with a certain amount of energy. If you want to break the crystal up, so again, breaking it up into ions, or imagine these free ions here are no longer in crystal form. Or if you want to, let me get rid of this arrow here. If you want to take the water and you want to separate the water molecules so that they can mix together, that's going to require some energy as well. So you're always putting in some energy when you're breaking a crystal and separating out water molecules. But once they mix together, they're going to recreate those forces. The water molecules are going to hydrate the ionic crystal. They're going to surround those charged particles, those charged ions, and that is forming a bond, an interaction anyways. And anytime you do that, you're going to get energy out. So anytime you dissolve a crystal, you're putting energy in to separate the water in the crystal, and you're getting energy out when the ions and the water start to interact. The difference between those two is the delta H, or the heat of solution. Now, sometimes you put in let's imagine this is all one level of energy, you put in a certain amount of energy, this one here, and you get out more energy. And in that case, you're going to have a negative delta H. But other times, you're at a certain energy level and you put in a certain amount of energy, as you always do, and you get out a certain amount of energy, but you've put in more energy than you got out. So in that case, your delta H here is also delta H, the heat of solution, but it is a positive value. So that's an endothermic reaction. So sometimes dissolving crystals is a exothermic reaction because the sum between the energy in versus the energy out is a negative value. And sometimes the delta H is going to be positive because the energy in is more than the energy out, and so the sum ends up being an endothermic change. All right, let's try out this question here. So in a calorimeter, there is 5.26 grams of sodium chloride. It's going to be dissolved into 100 milliliters of water. The temperature drops from 37.1 degrees Celsius to 31.5 degrees Celsius. We want to know what's the molar heat of solution for the dissolving of this sodium chloride. And again, we're looking for molar heat of solution. We don't need a whole mole though. We can just figure out from any amount and then later convert it into how much it would be for a particular mole. We know that the temperature is starting out as 37 and ending up at 31, so the temperature is dropping. The water that the crystal is in is losing energy as the crystal dissolves. We're also dealing with 100 mils of water, and so imagine we've got our water here and we've got our crystal inside of it, and as the crystal dissolves into smaller pieces, or essentially ions, the temperature is going to be dropping of the water around it. And we have a particular amount, so we've got to factor that in as well. We'll look at two ways of solving this, but I'm going to treat the system as the salt dissolving, because that's the molar heat of solution I'm looking for, and the surroundings in which it's occurring is the water. So first, let's try to solve this problem by breaking it up into little steps and then putting them together, and then we'll try again doing it all in one step. So the system itself, you can't measure the change in its energy directly. So between the ions when they're in a crystal and the ions in their water, it would be impossible to measure the exact energy values of those ions in both states. And so the thermometer essentially is sitting in this cup. And so imagine there's a thermometer that has the water inside. That's a thermometer. And the temperature is going to be dropping. So it's starting at something and it's ending up dropping because it's sitting in water, which is becoming cooler. So you can kind of think of it as if the thermometer itself is just like the water, part of the surroundings. And so essentially it is going to be losing energy into the crystal, which is going from a solid to aqueous ions. So that is the system, the crystal dissolving, and the water, and hence the thermometer as well, is the surroundings. So energy is moving from the surroundings and going into the system. That's why the water is getting colder. So we can plug in the values that we know for the water, and we can say, okay, well, we're dealing with 100 mils of water. We know its temperature change, what it's starting at and what it's ending at, and it's water, so we know its heat capacity. So we can figure out what that energy change is. What's the Q value? What's the heat that is leaving the water? So again, put in the mass of the water, and again, we're just converting the milliliters into grams. We're using 4.18 joules per gram degrees Celsius as the specific heat capacity of water, and the change in temperature, the final temperature minus the initial temperature, is going to be negative 5.6 degrees, and it's really important that you put that in as a negative. That way your answer will come out with the right sign on it. And so this ends up being negative 2,340.8 joules. That is moving from the water into the process of dissolving the crystal. Now, that's the Q for the heat that the water is losing, and we know that the Q of the water is going to be equal but opposite to the delta H of the system. So again, if the crystal, so let's draw this out visually, if we have some water and we have a crystal, let's do that in green, a crystal that is starting out as a solid and becoming ions, it's dissolving, we can see that the water is losing heat in order to allow this process to happen. So the crystal is going through an endothermic change. The water is losing the energy in order for this process to happen. So whatever amount of energy the water is losing is going into the crystal, and it will be the exact same amount of energy. We're pretending no energy is lost here, but it will be an equal value. So if the water is losing 2.34 kilojoules of energy, then the crystal must be gaining 2.34 kilojoules of energy. So we can make the statement that the delta H of the crystal, it's going to be a positive 2.34 kilojoules because it is gaining it. The crystal itself, going through dissolving, is an endothermic reaction. It absorbs 2.34 kilojoules of energy from the water. Now, that's the amount for 5.26 grams of salt, but the question is asking for the molar enthalpy of solution for the crystal dissolving. So we have to convert that into moles, which is fairly straightforward. We can take the mass and divide by the molar mass, and we're going to end up with, okay, we're not dealing with a full mole here. This is 0.0900 moles, and we can use the essentially the equation, if you want to think of it that way, that N multiplied by delta H of solution will equal the delta H of the particular situation that we're looking at. So we have this delta H for the particular situation, the 5.26 grams of salt dissolving. We just figured out the moles, and so now we can use those two numbers by taking the delta H and dividing by the number of moles, and that will give us our molar enthalpy. Now you don't have to memorize the equation because we have the kilojoules and we have the moles, and if you want molar enthalpy, then you just take the kilojoules and you divide by the moles, the 2.34 kilojoules, and you divide by the 0.0900 moles, and your answer is in kilojoules per mole, which is the molar enthalpy for this salt. So the molar enthalpy of solution, also known as the heat of solution for sodium chloride, is 26.0 kilojoules per mole. That's it broken up into steps. Alternatively, we can try to do this all in one step. We can say, okay, well, instead of dealing with sort of three separate equations or sort of looking at one at a time, what we can say is that we know that the molar enthalpy times the number of moles is going to be the change in enthalpy for the system in this given situation. And we know that we can take the values from the surroundings and we can plug them in. We know that the molar enthalpy multiplied by the number of moles is equal to negative mc delta T, because whatever energy the surroundings are losing, are going to be gained by the system. We are trying to get to the molar enthalpy, so we can rearrange, put N on the other side, and we can even replace N with molar mass and mass, just so we have replaced it. N equals mass, that's a little m, over molar mass, and so we've substituted N with mass over molar mass. Then we can plug in all our numbers we have from the question, our mass of the water, heat capacity of the water, and the temperature change of the water. So imagine that's our MC delta T as a negative. We're going to multiply that by the molar mass, divide by the mass, and in one single step, we're able to get down to the molar enthalpy of solution for sodium chloride. Make sure again that when you're using the change in temperature, you're putting in the proper sign. If the temperature on the thermometer of the surroundings is going down, then put in your delta T as a negative, whatever it is. If the temperature is going up, make sure that your delta T is a positive value because the temperature is going up. This way, when you work through the equation, your delta H will be what it's supposed to be. Some people treat the delta T as an absolute value and just say, okay, well, what is the temperature changing by, regardless of which direction it's going? But if you actually put in the direction it's going, then the math will give you the proper sign on your delta H. Otherwise, you just get an absolute delta H value and you have to state whether it is gaining or losing. Let the math do that for you. Just put the signs in as they actually appear, and the math will work out to give you the delta H as it actually is.